Okay, hi everyone. It's time, so I guess I'll get started. What are the people who are presenting today here? Okay, great, thank you. We have two people, I guess. So I'll leave plenty of time at the end. And if we have more time after that, I might talk about a few other things that aren't on the slides, but I'll make sure to leave time for you. So this time I would like to talk about chain of thought reasoning, and this is kind of like a fundamental thing that we use in most models nowadays, but it has some kind of like interesting properties that we definitely want to know about if we're going to be building models that do inference. And this will build into reasoning models, which are, like one of the most important technologies that we're working on now. Reasoning models and chain of thought models are basically, uh, reasoning models use chain of thought, but they're explicitly trained to be very good at using chain of thought. So you can kind of think of it as an extension of what we're going to be talking about today. Oops. Oh, sorry, 1 second. That is not moving for some reason. Sorry, I need to figure out how to remove this Zoom annotate menu. Okay, there we go. Okay, great. So our motivation for chain of thought is we want to do complex reasoning tasks, and this is an example of a complex reasoning task that I wanted to do for this class. What is the fastest an H100 GPU could possibly generate 100 tokens from Llama 3 8B? Anyone have an idea of how you would solve this? How would you start answering this question? Any brave person want to? I'm not asking you to answer it. I'm asking you how to start to answer it. Yeah.
You probably figure out how long it takes to blend those in.
Figure out how long it takes for one token, and how would you figure out the like lower bound of how long it would take for one token?
I think it's the same.
Oh, do it empirically? Okay, empirically is not the lower bound though, because there's all kinds of things that could, interfere with that. Like if you're using PyTorch, maybe you have overhead from PyTorch, and if you use something faster that was written in Rust, maybe it would be you'd be able to do it. Yeah.
The number of
Yeah, determine the number of computations, and you know the number of computations that an H100 GPU could do from the GPU spec, and then you could calculate the number of floating point operations that are necessary for one token. And having one token would not tell you the whole story. Like why would having one token and then multiplying it by 100 not tell you the whole story? Any ideas? Yeah.
attention takes longer, so further you go.
Yeah, because attention has quadratic computation time. So yeah, that's true. And then this is still a lower bound, and there's actually upper bounds because you're not like fully utilizing the GPU, because when you generate one token at a time, you have to wait and then generate the next token and stuff, which is also why encoding is faster than decoding. And we'll talk about all that during the efficiency. But so if you ask a language model to do this, it will have to do a lot of things like you did here. So it'll have to recall what the flops of an H100 are, or search it on the internet. Another tricky thing is, depending on your floating point precision, the flops differ on an H100, but we could ignore that for now. And then what's the size of Llama 3 8B for each of the layers? It would have to think about how it could set up a computation. So it would have to think about, like, how do you calculate the flops given the size of Llama 3 8B? And then it would have to perform the actual computation itself. And so it could either perform the computation by, like, having the language model do the computation, or it could run a program that does the computation for you. Write a program and then run a program that does the computation for you. So we're going to talk about reasoning models that are capable of doing that computation on their own in about, like, 2 classes. And then we're going to talk about the running a program for you part in about, like, maybe 3 or 4 more classes. So, all of this we will be talking about in the future. But the fundamental challenge here is that not all problems are created equal. So the problem that I just gave you is a really hard problem for probably everyone in this class. Like, you probably could do it if you really put your mind to it, but it's not, an easy one. On the other hand, I very much hope that this is an easy problem for everybody in this class. Otherwise, you're in the wrong class. This one probably is also easy for most of us. And this one, is easier than the GPU problem, but it's, you'd have to think about it a little bit and maybe pull out a piece of paper and stuff like that. So another thing is the simple problems you should be able to solve very quickly by just thinking. Like, you might not even really feel like you need to think. If I tell you 2 + 3, you just say 5. You don't, like, need to work through it. If for the medium and complex ones here, you probably would need to think about it and, like, kind of write out the equations in your head or on paper and solve them. And that's the same for language models. So a key question is, how can we allocate computation based on problem difficulty? And, like, another way to think about it also is there are problems that, like, just fundamentally could not be solved by feeding in an equation and predicting the output, because they are more computationally complex than all of the computations that you do in predicting a single token in the language model. So, like, it's theoretically impossible to solve all problems with a single step of a language model. But that's not usually the problem. Usually you still have enough computation in a single step of the language model. Calculate the number of flops that you use when you calculate like the next token in Llama 370B, and it's a huge number of flops. So it's more just that language models are not particularly accurate or efficient at solving computation problems. Cool. Is that clear? Any questions or? Okay, so before we go into, like, transformer language models, I'd like to point out that this is not an idea that has just suddenly popped up overnight. There's an idea of adaptive computation time, which, for example, was put out in recurrent neural network language models by Graves in 2016. And the idea was that you dynamically adjust computational effort based on the input complexity. And the way they did this was they taught recurrent neural networks to learn how many computational steps to take. And so they basically had a halting mechanism. And the way the halting mechanism worked was, if you had the hidden state of a recurrent neural network, you would run it through basically an MLP, not MLP, you would run it through like a sigmoid style predictor that would then predict I should stop or I should not stop. And then after you ran that, you would then decide whether to stop or not. And they also trained it with something they called the ponder cost, which was basically how many steps, a continuous approximation of how many steps you took to encourage efficiency. And they demonstrated that this, worked on a variety of problems back then. You can see this and see figure 1 in the paper if you'd like to see how they created the network and stuff. So this was a more explicit version of doing adaptive computation time. But there, the more popular version of it is now, of course, LLMs, because we use LLMs for everything nowadays. And chain of thought prompting is something that came up within LLMs. And it's kind of interesting because it's an emergent property of language models and not necessarily something that you need to explicitly bake into the model. And so the basic idea is that you want to generate intermediate reasoning steps before producing the final answer. And the formal definition, which we will be using as we explain different methods later, especially for training, is that we have the input X, which is our problem statement. We have the chain of thought Z, which is our intermediate reasoning steps, and we have the output Y. And this is also what I covered in the first class here. But basically, Z is a latent variable that we use to improve our predictive accuracy of Y. Okay. So basically what our goal is we want the best P of Y given X. So we want the best predictor of the output. But the way we will do this is we will do this by marginalizing over Z. So summing over all Z so that we can get a better prediction of Y. So this has a number of advantages. Number one, the extra tokens provide adaptive computation time, like I mentioned before. So you can spend more flops when you're calculating the more difficult problems. Another advantage of this is if the chain of thought is faithful to the actual reasoning, it makes it easier for humans to verify the output. So like a human can walk through step by step and check if they fully understand, what the model is generating step by step and verify it as well. So here's an illustration of a chain of thought specifically from the Way et al. Paper. And if we look at standard prompting, this is standard few shot prompting. So basically we're providing a few examples. So we have like Q is the question, A, the answer is whatever, Q, the question, A, the answer is whatever. And so chain of thought prompting is Q, and then you also have an explanation for how you got the result. And then the idea would be that because the model has seen this before, the model is able to generate the output like this. So, yeah, and so let's look at few shot chain of thought prompting. Or sorry, I thought I deleted these deleted these slides, but they were not deleted. Okay, so then the question is, how do models learn chain of thought? And there's a number of different ways you could do this. In the Way et al. 2022 paper, they discovered that even without teaching the model or training the model in any way to do chain of thought, it was able to do that. Does anyone have an idea why the model had this ability to do chain of thought in the first place? Yeah.
All many instances and sequence of events in data in logical order.
Mhm.
Already like a notion of a sequence of deductions following from premise.
Okay. So training data already has examples of sequences of deductions. So I think that's a great point. We could be even more concrete. What type of data would have a lot of this? Code might be one example, yeah. Stories. Proofs, yeah. So online proofs or online elementary school math textbooks, which is like where they give you this deduction and they evaluate on grade school math. And there's a ton of grade school math online that has these deductions like explicitly written in it. So the models might not necessarily do that by default, but if you provide them examples to demonstrate that they want to do it, they might just be able to do it. And so this is an emergent ability because this already exists in the training data, and this appears in sufficiently large models, or I should say sufficiently strong models. So these sufficiently strong models were like GPT-3 175B in 2022. Now they're like Quen 2.5 1B in 2025. So it's like a lot of models. A lot of models have just gotten better due to longer training and other stuff like this. Another thing is supervised fine-tuning. So this is done by training on data sets that explicitly have reasoning steps written in them, so that using supervised fine-tuning. So I should give a little bit of a caveat here because this is kind of important, and maybe we'll talk about it a little bit later. But when you get large language models, there's often like the base model and there's the instruct model. Probably people have seen this if you've used large language models before. So like Llama 3.1, Llama 3.1 or Llama 3.1 base. Sorry, Llama 3.1 instruct or something like that. One small problem with this is now there's a concept of pre-training and post-training. So pre-training is like your base model, post-training is your instruct model. But now people are doing something called mid-training, which is basically where you pre-train the model and then you throw in a lot of data that's like very high quality by some definition of high quality right at the end of pre-training. And this idea of very high quality might be particularly instructional data, which is data that's like very similar to textbooks or something like that. So our base models are now half like supervised trained. It's like maybe not exactly supervised, but it's pretty close to supervised. And so because of this, things that might seem like they've just emerged in the base models actually already were there because they were, the people who pre-trained the models very carefully selected the data they showed at the end of training. So some of the models are kind of in the middle, and this is particularly like Quen. The Quen model is particularly famous for this. So there have been a lot of examples of people seeing quote unquote emergent abilities in Quen that you see in no other models. So happy to talk about the details of that, but that's an important thing that people have been talking about nowadays. A final thing which we're going to be talking about in the reasoning model section is reinforcement learning. And so there's been a lot of work recently where we basically ask the model to do reasoning, and then we give it a reward if it is successful at answering questions. So these are the three major ways that they can learn how to do chain of thought. Any things here? Yeah.
Sure that very marginalizing over change. So if you got mathematical understanding correct, you're like looking at all possible chains of thoughts from X.
Yeah, I'll talk about that in a second. Yeah. Cool. So if we look at the experimental results, and actually maybe I should mention this here. So what they are doing in this paper is they're not looking at all chains of thought. They're just sampling one or taking the doing greedy decoding. I think they're sampling with like sampling parameters. I actually should know that, but I don't. You can take a look at the paper and check. But basically what they demonstrated was that on arithmetic reasoning, GSM 8K, this is a data set of grade school math problems, and they get a very large improvement. On common sense reasoning called strategy QA, strategy QA was kind of created so that you should need multi-hop reasoning to do a good job, or kind of like complex reasoning strategies to do a good job. They also saw a good improvement. And then for symbolic reasoning, where they were like concatenating the last letter of particular sequences, they also got good results. And so we saw the biggest gains in things that are like very symbolic, like math or like kind of last letter concatenation. Cool. So this paper was really impressive because it's very simple. You just add zero-shot examples and the model is able to reason. Now we take it for granted, more or less, like every model does this. What was even more like impressive was this paper, which was kind of crazy, but it demonstrates that language models can learn kind of crazy things from the data that is provided to them. But this demonstrated a zero-shot chain of thought, where essentially instead of providing per task examples of how reasoning should happen, they just said, let's think step by step is the prefix to the answer. And then that was enough to encourage the model to basically do chain of thought reasoning. Um, and the funny thing is, let's think step by step is actually kind of magical. They evaluated a whole bunch of other prompts, and none of them were as good as let's think step by step. This is the magical one, but I also know one of the authors of the paper, and this was the first one they tried. So it turns out that human intuition is a kind of impressive thing that they actually got the best one on their first try. But so they basically demonstrated that you don't even need to have the examples to make this happen. Cool. Okay, so I'd like to talk about inference because this is an inference class, and this is really important. It's especially more important once we start using reasoning models that generate very long chains of thought. But if we remember back to the beginning of the class, our goal for inference is either to sample from the model, or to do mode-seeking search, so to find the highest scoring model output. So sampling, as always, if we want to sample exactly from the model score, the model probability is straightforward. As we mentioned before, ancestral sampling with a temperature of 1 is going to always be good enough in an autoregressive model. So basically, we sample z tilde, we sample the chain of thought, and then based on the chain of thought, we sample sampled output y, and we're done, basically. But mode seeking is harder. And so mode seeking or finding the argmax of the output given given the input is essentially what we need to do. I didn't put this on the slide, but we need to do this. So we need to find the y where the sum over all z that lead to y is maximized. And this is hard because how many z are there? How many possible z are there?
Wait, is we find the y for which sum of the z?
Correct. That's the what we would like to do. Because we want to find the y with the highest probability. Yeah. So how many z are there? Let's say our chain of thought is up to 100 tokens.
Okay,
Yeah, it's essentially it's close to v to the power of 100, and you're not going to be enumerating all of those, right? So we need another method. So we're going to be talking about more complex methods to do this in the lecture on minimum Bayes risk, but a first attempt. Oh, actually, sorry. Let me go to this first. So a first attempt is to find the argmax jointly over over z and y. And what this means is we just find we do like beam search or something like that to try to find the highest scoring output like we have previously, or best first search, whatever we want. But the problem is the argmax over z and y might not give the best y's. So for instance, if we ask how many inches are there in 3 feet. And we have, for some reason, a crazy model that decides to talk about centimeters instead with a high probability. Then this one would be the highest, zy, but it would not be the highest. It would not lead to the y with highest probability because, if you sum all the probabilities that lead to y, then y equals 36, you would get 0.6, where this is 0.4. So like there are plenty of situations where just doing this argmax search is not ideal. So the method that we can use to fix this is self-consistency, and self-consistency only works in relatively simple cases like mathematical reasoning, where it's like we have a single answer that's an integer. It will not work when we're generating essays or something like this, and that's where we need to get into something like minimum base risk. But for this, for self-consistency, if we have like the answer is 14 or the answer is 18, what we can do is we sample a whole bunch of reasoning paths, and then we basically count to see which answer is the most frequent. And based on the count where the answer is the most frequent, we take that as our answer. So it's not that hard. It is expensive though, because if you want to sample 100 of these, then it's 100 times the inference cost. Cool. Any questions here? And basically self-consistency on anything where we have this sort of characteristic that we can verify the outputs, it does better, but is more expensive. So because it's doing the right thing, so of course it does better, but it's also not necessarily the most efficient way to do the right thing. So there are better ways to do this. And this is actually a paper by Pranjal Agarwal, who's a PhD student in LTI, called Adaptive Self-Consistency. And basically, the way it works is you start sampling a smaller number of samples. And once you've sampled a large enough number of samples that you're pretty confident in the final result, then you will stop sampling. And the way they do this is they use like just a little bit of statistics, specifically Bayesian statistics, and they gradually generate samples, and they stop when the possibility of agreement of the final sample being high. The agreement of the final sample being, let me start over. When the probability of the final sample you get after sampling an infinite number of samples is above a threshold. So what that means, the way they do this specifically is they have a more complex version using something called a Dirichlet distribution, Dirichlet prior Dirichlet distribution. Have people heard about this in general? Oh, actually, surprisingly few. Maybe actually, I would like to talk about this because it's a good concept to know about. I don't want to mess up. I don't want to mess up the equations, but basically, what this is it is a prior probability that you can put on. It's a prior probability that you can put on discrete distributions, and so what that means is you essentially you can go through all of the math on Wikipedia or a tutorial or something like that, but you essentially start what it boils down to. is typically if you take a maximum likelihood estimate of an like probability distribution. Let's say it's a probability distribution over A, B, or C. Your maximum likelihood estimate, like let's say you've observed 1A and 0 Bs or 0 Cs. What's the maximum likelihood estimate here? It's not a trick. You've observed one example of A and 0 examples of B and C.
A.
Yeah, but what's the probability of A? 1, right? Yeah, 1.0 and 0 of 0. So what do you think the next letter is going to be? You've seen 1A.
A.
Do you think it's going to be A? Could it be B or C? It might be B or C, right? Like you're not very confident. Another way to think about it is you go to a new country and then you see that it's sunny the first day. Do you think it's going to be sunny for eternity for the rest of the time? Probably no, right? So what the Dirichlet distribution allows you to do is it allows you to put a prior on the probabilities, and then basically adjust to your observed data as you get more observed data. And so the easiest way to think about it is you have your observed count of I plus alpha times P of I. And this is the P prior. So if you say, I have no opinion about whether A or B or C is going to be more frequent a priori until I observe data, then basically P prior I would be 1/3. It's like all of them would have a uniform probability. And you can actually set, if you have a reasonable idea about what it might be, like let's say you believe that it's going to be more sunny than rainy, you might set sunny to 0.75 and rainy to 0.25 or something like that. But let's assume that we're working with a uniform prior. Then you take your actual counts, and if alpha is higher, you rely on the prior probability more, or you're influenced by the prior probability more. If alpha is lower, you're influenced by the prior probability less. If alpha is 0, this is maximum likelihood estimation. So if we set alpha to 0, it would just reduce to the counts, the actual counts divided by the sum of the actual counts. But like, let's say we set alpha to 3. What that would mean is our actual observed counts would be 1.000. The counts after multiplying 3 by 1/3, the uniform probability would be 2, 1, 1. And so based on this, we would then say the posterior probability, which is the probability after we consider the prior, would be 0.5 for A, 0.25 for B, 0.25 for C. And that's much more reasonable, right? You're not saying the probability of B or C is 0 because you've never seen it before. But let's say you see 10 Bs in a row or 10 As in a row. Now you're much more confident that you're not going to be seeing more Bs. So this is what that allows you to do. And this is like, that's kind of the illustration here. And another like advantage of this is like, as you add more evidence, it's still a Dirichlet distribution, so you can add that in. It's called the conjugate prior if you've done Bayesian, if you're interested in Bayesian statistics. But anyway, so this method basically used an idea like this. This method basically used an idea like this, and they actually introduced the Dirichlet distribution as their like initial motivation, but then they simplify it to use something called the beta distribution. And the reason why they use the beta distribution is calculating the Dirichlet distribution over the entire vocabulary can be kind of expensive, but they can calculate this beta distribution over just the number one and number two probabilities. And then once they have done this, they can calculate whether the probability of one being of the number one output continuing to be true after you sampled more information being over a particular threshold. And then they stop at that point. And they set this threshold to 0.95, which basically says I have 95% confidence that if I sample more, I'm not going to get a different result. And so that's how they did this. Yes. It's calculated after each batch of generations. And I don't remember the exact schedule they'd used to do that, but basically the idea is as you can keep calculating until you get more certain about until you get certain enough about the output. P2 is the probability of two, and then V2 is the number of instances of this. Sorry, P2 is the probability of the second most probable output, and V2 is the count of the second most probable output. V1 is the probability of the first most. You can look at the paper for the full derivation of this. Cool. Okay. So I think this is a really nice inference algorithm because it basically demonstrates how you can adaptively use compute, maybe in the other dimension. So like chain of thought is adaptively using compute by generating more tokens. This is adaptively using compute by generating more hypotheses. So it's kind of a cool trick that you can do to save compute. But I'd also like to talk about some features of chain of thought reasoning. So the first thing is, of course, when people write papers, they want to show that their method is useful. And so they choose test beds that demonstrate the strength of their methods. I don't think that's a bad thing. I think that's a good, it's good to do this, but this paper is a little bit of it basically demonstrates that CoT is not useful all the time. And in fact, it's not only not useful all the time, but in kind of more traditional models, it was only useful for like math and logic. And this is something that I think a lot of people kind of knew already, but nobody talked about. But then this paper talked about it. So now we can't not talk about it anymore. But basically, they did number one, a meta-analysis of 100+ papers that were using CoT, and they basically looked at the types of things that they evaluated on and how big the kind of gains were. And then they did an actual evaluation with 20 data sets across 14 models. And maybe I'll just jump directly into the results. This is maybe a little bit hard to see. But basically, the ones on the bottom are math. These are deductive reasoning style benchmarks, like specifically made to create deductive reasoning, to measure deductive reasoning. And then a lot of these others are like common sense QA, strategy QA, kind of word puzzles or common sense puzzles, things like this. And what you can see is there's this huge gain for like math questions and quite a bit less. Oh, in green is chain of thought and blue is non-chain of thought. And what you can see is there's a huge gain on things like math and deductive reasoning and much less impressive gains on a lot of the others. So this is a good thing to know. What it means is if you want to use reasoning models, you should probably try them on math first. Another thing it means is there's a big opportunity for coming up with more generalizable reasoning strategies that are also helpful on other tasks or correction strategies or things. And I'm doing a little bit of research on this now. Other people are thinking about it, but happy to talk more about that. I thought this was rather clever. Basically, what they did was they took MMLU, which is kind of a data set of lots of college level questions, and they found all the questions that had an equals sign in them, or in the answer or something like that, and all the questions that didn't have an equal sign in the answer. And basically, the lighter bars are the ones that had an equal sign, and the darker bars are the ones that didn't have an equal sign. And so what you can see is people were saying, oh, chain of thought reasoning helps on MMLU, but basically it only helps with the math in MMLU, and like all of the others, it was not helping with very much. Cool. Any questions? Okay. Another thing I'd like to talk about is the faithfulness of explanations. And this is also a really clever paper, but I mentioned that one of the advantages of chain of thought reasoning is that if the explanations are faithful, they can help humans understand the reasoning process and verify whether the output is correct or not. But there's a big if there that, that's if the explanations are faithful. So if we look at chain of thought explanations and whether they actually reflect the reasoning process, they did a clever trick here where they basically introduced subtle biases into the few shot examples that influence the model predictions. So for example, they reordered the multiple choice options so that every multiple choice option was A. And so all of the examples were A. And then they asked models for CoT explanations of their bias predictions and tested faithfulness. And here's an example where basically they have the unbiased context and the biased context. And the question is the following sentence plausible? Wayne Rooney shot from outside the 18. Answer choices A, implausible, B, plausible. Let's think step by step. And in the unbiased context, it got the answer correct and said Wayne Rooney is a soccer player shooting from outside the 18-yard box is a part of soccer, so the best answer is B, plausible. And then in the biased context, it said Wayne Rooney is a soccer player shooting from outside the 18 is not a common phrase in soccer. And 18 likely refers to a yard line, which is part of American football or golf. So the best answer is A, implausible. This is the same model, right? So like when it's not biased, it's able to answer with a faithful explanation. But when it is biased, it will answer the wrong thing with an explanation that looks plausible but is wrong. So, and of course, this is not just a problem of like when it's biased, it's a problem in general when it gets it wrong. But this is a particularly like obvious example of this. That being said, this was on Claude 1.0 in 2023. Models have gotten a lot better at not doing this as much, but they still do it when they're out of distribution or on topics they're not familiar with and other things like that. Like I remember I asked GPT-4 how many parameters GPT-4 had, and it said GPT-4 does not have parameters per se. Like, yeah, and they found accuracy drops and also models generate confident explanations for both correct and incorrect answers. Cool. So another example, this also goes into what we're going to talk about with reasoning models. But one feature of chain of thought is that longer chains of thought tend to be better on average. And so this is a paper from 2022 where they demonstrated that even with very early chain of thought models, longer chains of thought tended to be better. So these are not models that were trained for chain of thought. These were only the ones that had like emergent reasoning. And so this is an example where they basically took the more simple and more complex chains of thought that they got. And there was a pretty strong trend that the accuracy of the final answer increased when the model generated more complex chains of thought with more sentences. And so based on this, they came up with a really simple method called complexity-based prompting. And what this meant was they basically generated a whole bunch of chains of thought, and then they deleted the ones that were shorter. And then they did self-consistency over the outputs. And this very simple trick resulted in quite a bit. Whoops, lost snap. My slides have crashed. Okay. So the results, they saw pretty large accuracy improvements on average. And this was robust under format perturbation and distribution shift. Yeah, sure. So basically what they did is they generated a whole bunch of chains of thought, and they looked at the number of steps, like the number of sentences basically in the chain of thought. And then they just deleted some of the shorter ones and then did self-consistency over the longer ones.
For some questions, suppose we have n sentences, and for suppose we have n by 2 sentences, which ones did you delete?
They deleted the ones that had fewer sentences in the chain of thought. And so the model can kind of like, they were sampling from the model, and the model can generate different length chains of thought, and they empirically observed that longer ones tended to be better. So they just deleted the shorter ones. I mean, there's probably better ways to do this, but I think it's still pretty clever that it actually worked. Cool.
So kind of the max for the express seems to be awkward in that like you're marginalizing all the chains of thought, and yet the longer our chain of thought is, so like the search space explodes that much more.
Yep.
And yet you're increasing increments in performance. There's like something going on. Are we really when we provide a chain of thought? Is the reason output really influenced by some sort of marginalization over all possible chains of thoughts, or is it more like a chain of thought is helping scope out some sort of it's able to define the search space? It's rather
So the big assumption behind chain of thought is basically that we have P direct, which is just P y given x from the LM. And then we have P CoT. So these are actually two different probabilities, right? And the bet is that essentially this is a better probability. This will give a higher score. I have to think like a little bit about exactly what probability this corresponds to. It's some variety of like rejection sampling or something like this. But this also is giving us a probability over y given x by some sampling and then removing the lower, smaller length samples, basically. And the bet here is that that's an even better probability. And what I mean by better probability is because we're like self-consistency, for example, is basically trying to take the argmax of the probability. And so if you take the argmax of that, the error will be lower, is what I mean by better.
like you see that even if you have just one chain of thought, one thought, not doing self-consistency, you're not doing this sort of rejection sampling.
Yep.
You see the math coding tasks, logic tasks, like performance just straight truth sum. So it's not this marginalization, it's simply P z particular y given x is better than P of y given
Yep.
x.
So one thing I will say is having just one example is a really bad form of marginalization because you're still sampling from the model. It's just one sample is not a very good estimate of the marginalization, but it still is an estimate of the marginalization because like an estimate of the true probability because you're sampling when you sample, you're estimating the kind of probability. Yeah.
I think the two right-hand sides are actually equal by law of probability. So there must be some other explanation for where is it.
The two right-hand sides are not. I need to. I might need to fix this somehow, but they're not equal because essentially this. I'm trying to figure out the best way to write this, but basically like y coming after z has a different probability than y like not coming after z.
Oh, I see. So it's yeah, it's the ordering now.
Yeah, like the fact that z exists influences the output. Yeah, so sorry, my terminology is my formulas are not very good, but I'll have to think of a better way to fix it.
Select steps below which you are user in the sample.
How do you select the number of steps? I guess one answer is how much compute do you want to spend on doing this? Because generally the accuracy will just go up as you sample more. It will eventually plateau and then it's not worth doing it anymore. Are you talking about specifically for this method?
Yeah.
So this method's pretty heuristic, honestly. So I think if you wanted to adjust the hyperparameters, you would mostly have to do it empirically, but there probably are better versions of this. And so like actually we're going to be talking about like reward models later. And essentially this is also kind of a really heuristic reward model that's saying longer ones must be better than shorter ones. And there are like better ways to come up with reward models that like actually predict whether the chain of thought is good or not. Yeah.
And the faithfulness thing, like you said that with baseline models, it's fixed for like that the reasoning along with the like final answer. But
It's better. It's not fixed for reason models. Yeah.
this doesn't hold true for multi-step scenarios. Like let's say we have an agent going things and like they like trajectory doesn't necessarily.
Oh, yeah. I said it's better. It's definitely not fixed. And so you said in multi-step scenarios, it's not good. Yeah, I think agents do lie to you all the time, is my experience. So it's not definitely not fixed. Cool. I definitely want to leave time for our student presentations also. So another thing is chain of thought can be used multimodally as well. The early attempts to do chain of thought like multimodally were basically like you write down you take a vision model or you take a vision input and a language input, and then it comes up with a rationale and predicts the output, and the results are much better. Also, I'm not super familiar with these, but I have seen a few papers where like they actually try to find bounding boxes that they incorporate into the outputs as well. So if you're interested in multimodal stuff, there's a fair amount of work on this as well. Cool. And so just looking a little bit into the future, next we're going to talk about self-refine and self-correction models, the methods which kind of go back and correct previous outputs, and then we're going to put the two together into reasoning models in the following class. Yeah. 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 The fact that it's an emergent ability is due to the pre-training data. I would say that most models nowadays are also trained on large amounts of SFT data. But it being an emergent ability is like kind of one of the really exciting things about reasoning models. So like there was a paper on DeepSeek R1 where they basically demonstrated that you could take mostly a base model with very little SFT data, and it's still able to learn how to reason. And I think that comes from the emergent ability of the models from the pre-training data. Cool. Okay. Thank you. And we'll have the two presentations next. If you could come up and